The attached table shows benchmark results for different machine learning methods on the BreastMNIST dataset, evaluating both AUC and accuracy metrics. ResNet 18 at 28 by 28 resolution achieves an impressive AUC of 0.901 and an accuracy of 86.3%, which is slightly lower than Google AutoML Vision's AUC of 0.919, but comparable in terms of accuracy. The ResNet 50 models, while performing slightly worse overall, still offer competitive results. AutoML methods like AutoSclern and AutoKeras show solid performance, making them viable alternatives for automating model optimization. Given these benchmarks, your goal to replicate or improve upon such results is ambitious yet achievable. Using a pre-trained ResNet 18 or ResNet 50 as a baseline for transfer learning could help you reach similar performance metrics, particularly if you adapt the model to the 224 by 224 resolution used in your data. This requires training on your specific dataset with class balancing techniques and careful hyperparameter tuning to prevent overfitting, especially given the label imbalance. For deployment, separating the performance display from the image prediction interface is advisable, as it keeps the application lightweight and modular. Initially, you could implement a performance dashboard like the one in RhythmScan to showcase metrics, visualizations, and sample predictions. Later, add a separate page for user-uploaded image predictions, leveraging TensorFlow.js for client-side inference. This division will ensure a smooth user experience while maintaining high functionality.
Can you also explain how is it even possible that the ResNet 18 performed worse with more pixel data, with higher pixel resolution images?
It may seem counterintuitive that ResNet 18 performed worse on higher resolution images, 224 by 224, compared to lower resolution ones, 28 by 28, but there are a few plausible explanations for this. 1. Overfitting to noise in high-resolution data. Higher resolution images include more pixel data, but not all of it is necessarily useful for classification. This additional data can introduce noise or irrelevant details, causing the model to overfit on these less significant features and perform worse on unseen data. 2. Model capacity versus data complexity. ResNet 18 has a relatively small capacity compared to deeper architectures. While it can effectively handle low-resolution images by extracting key features, higher-resolution images may overwhelm its limited capacity. This mismatch means it may not learn the additional details effectively. 3. Preprocessing issues. If the dataset at 224 by 224 was not preprocessed properly, such as inadequate normalization, resizing artifacts, or inconsistent augmentation, it could negatively impact model performance. For instance, resizing from 28 by 28 to 224 by 224 may stretch or distort important features, reducing their clarity. 4. Task-specific patterns. For this dataset, the key features distinguishing benign from malignant may already be well captured at low resolution. Increasing the resolution might not add meaningful information, but instead amplify irrelevant details, making the task unnecessarily complex for the model. To address this, you might explore techniques like fine-tuning a larger model, e.g. ResNet 50, for 224 by 224 data, optimizing pre-processing pipelines, or using dimensionality reduction techniques to focus the model on relevant features.
Hey, can you quickly summarize the last response, like in 2 sentences?
ResNet 18 likely performed worse on higher resolution images because the additional pixel data introduced noise or irrelevant details, leading to overfitting, while the model's capacity wasn't sufficient to handle the complexity of larger images. Additionally, the low-resolution data might already capture key features, making the higher resolution unnecessary for this task.
Okay, can you give a quick summary for the whole conversation, just in case someone joined us live right now? Just a quick summary without the fluff for the whole thing.
We discussed adapting a BreastMNIST training pipeline without Flask, focusing on client-side deployment using TensorFlow.js for image classification. Key points included normalizing data, handling class imbalance, benchmarking against ResNet models, and displaying model performance metrics on a lightweight web interface, with plans to separate performance visualization from user-uploaded image predictions.
Okay, can you ask me questions about what I uploaded so far and about how we prefer moving forward?
Do you plan to replicate the high-performance ResNet 18 results from the benchmarks or experiment with other architectures like ResNet 50? How should we handle the dataset's label imbalance? And would you prefer focusing on class weighting or augmenting underrepresented classes? For the HTML interface, do you want to separate performance metrics and user-uploaded image predictions or combine them into one page? Lastly, should the application prioritize lightweight deployment with pre-trained models or support client-side training as well?
No, I think so. To the last question, I think client-side training will be too much. What do you think?
I agree. Client-side training would be too resource-intensive for most users, especially with a dataset like BreastMNIST and models like ResNet. Pre-training the model and deploying it in TensorFlow.js for client-side inference is a much better approach. This keeps the application lightweight while still allowing users to upload images and get predictions efficiently.
Okay, what were the other questions, the previous questions?
The other questions were, do you want to replicate the ResNet 18 benchmark results, or would you prefer experimenting with architectures like ResNet 50? How do you want to handle the dataset's label imbalance by using class weighting or augmenting the underrepresented class? And for the HTML interface, would you prefer separating performance metrics and user-uploaded predictions into two pages or combining them into one?
So what do we currently have in the code? What are we using for training at the moment?
Currently, the code uses a custom CNN model with 3 convolutional layers for training, along with data augmentation and class weighting to handle label imbalance. It also includes callbacks for early stopping and checkpointing, and it saves the trained model in both .keras and .h5 formats, with an option to convert it to TensorFlow.js for deployment.
Okay, that sounds really good. How is it better or worse than ResNet 18 or ResNet 50?
Your custom CNN is simpler and lighter than ResNet 18 or ResNet 50, making it faster to train and less resource intensive. However, ResNet architectures are more powerful due to their depth and residual connections, which help them learn complex patterns and avoid vanishing gradients. For BreastMNIST, ResNet models might perform better at capturing subtle features critical for classification, especially on higher resolution data.
Can you go into the details some more? What's the difference? So what do we currently have? Like how many layers, so on and so forth, and compare it to ResNet 18? I thought ResNet 18 will be actually a fairly simple model.
Your current custom CNN has 3 convolutional layers, followed by max pooling and fully connected layers, making it relatively shallow. Each convolutional layer extracts basic features, while max pooling reduces dimensionality, and the dense layers perform the final classification. This simplicity makes it fast to train, but limits its ability to capture complex hierarchical features. ResNet 18, while simple for a ResNet, is much deeper, with 18 layers of learnable parameters. Its key advantage is the use of residual connections, which allow the network to skip layers and preserve gradients during backpropagation. This architecture enables the model to learn deeper feature representations without suffering from vanishing gradients, making it more effective for complex patterns like those in high-resolution medical images. In comparison, your CNN, 3 convolutional layers, shallow depth, no skip connections, simpler and faster to train but limited in feature extraction. ResNet 18, 18 layers, deeper architecture, residual connections, more computationally intensive but better at capturing subtle and complex features. While ResNet 18 is relatively simple compared to ResNet 50 or deeper models, it is significantly more powerful than your current model due to its depth and use of residual learning.
So I generally don't want to go for a complex model without any specific need. I would like to actually train quickly with what we currently have, and yeah, we'll just go from there.
That makes sense. Starting with your current CNN allows for faster experimentation and iteration. If the performance is sufficient, there's no need to move to a more complex model right away.